Welcome to today's webinar. Our topic today is indoor navigation. My name is Joe Winans, and I will be your event manager today. Before we get started, I want to let you know about today's webinar that we will be recording the session, and currently you are in a listen-only mode. At this time, I'd like to acquaint you in which ways you can participate during the presentation. Please notice in the lower left-hand corner of your console that there's a Submit button. We encourage you to ask questions throughout the presentation. Just type in the text box at the bottom left and click Submit to place your question in queue. Most of the questions that were submitted during the registration process will be covered in this webinar or perhaps covered in an upcoming issue of one of our GPS World e-newsletters. And if you experience any technical difficulties during today's event, select Help to submit your issue, and we will assist you. Now, without further delay, I'd like to turn today's event over to our moderator, Alan Cameron.
Hi, everyone. It's Alan Cameron, Editor-in-Chief of GPS World Magazine, and welcome to today's webinar on indoor navigation. I'd like to thank, first of all, our sponsor, Hemisphere GPS. Hemisphere has sponsored the full year of webinars on gpsworld.com. This is our 12th, at least, to date, and most of these webinars, at least the recent ones, are still available for download at gpsworld.com. And we look forward to another exciting year of webinars beginning in January. Today's topic is indoor navigation. Indoor navigation, of course, has been a topic of interest almost since outdoor navigation began, outdoor GNSS navigation, that is, back in the 80s and 90s. But it's really come on strong in the 21st century because indoor navigation is where GNSS has the most difficulties currently, but where it has to go in order to be truly commercially, governmentally, and societally effective and integrated into modern life. GNSS, as most of us know, is challenged to function, to provide reliable and continuous positioning accuracy indoors, and those difficulties, those challenges, are the topics that we're going to address in today's webinar. This is kind of the climax of a crescendo of recent indoor positioning presentations in GPS World. I refer to a story in the November issue by two of our, or one of our presenters at least, here today, Blake Bullock. We had an article on continuous indoor positioning, GNSS, Wi-Fi, and MEMS dead reckoning in the November issue. Then also toward the end of the month in November, I wrote a newsletter column, a system design and test newsletter column that you can find at gpsworld.com under the GNSS pull-down menu, Getting to Z, Indoor Positioning with GPS, and that concerned a very important series of trials currently underway in the Bay Area on the efficacy of various methods of assisting or augmenting GPS with other technologies. We're going to have 4 speakers today for you, and they're each going to talk for about 10 minutes, and then we should have time at the end for your questions. As mentioned earlier by Joe, you can submit questions during the webinar itself. I will see those questions and make a selection. We also have a number of questions that many of you posed as you registered for the webinar. So we'll have a 10 to 15 to 20-minute question period after the speakers. First, we're going to hear from two of our 4 speakers. I'm going to present sort of jointly or continuously. First, we're going to hear from Dave Huntingford, Director of Product Management, Location Products at CSR. Dave's a 15-year veteran of the location business. He is responsible for the location product portfolio at CSR and its expansion into GNSS, wireless hybrid, and MEMS motion capabilities. He previously worked with Surf and Motorola. He has a Bachelor's of Science from the University of Hertfordshire in the UK. And continuously with him, or segueing with him, we'll hear from J. Blake Bullock from Samsung. He was a senior product manager responsible for CSR's next generation of GNSS solutions. He's now transferred to Samsung. They'll address the migration, so to speak, of GPS from SURF to CSR to Samsung in their talk. Blake holds a Master of Science degree in Geomatics Engineering from the University of Calgary, an MBA from Arizona State University, and several patents in LBS and navigation. I'd like to turn it over now to Dave Huntingford. Take it away, Dave.
Okay, thank you, Alan, for the introduction. So let's move to the next slide, and maybe a quick word of introduction about what's happening between CSR and Samsung. So recently we completed a transaction where we transitioned our handset connectivity capability and a seed team for handset location development to Samsung LSI. And this deal was a total of around 300 employees transferred to Samsung, including Blake Bullock. And Samsung intends to take this technology from that seed team and the designs given to them and start to integrate it into their application processors for the handset market. And an important part of this transaction is that we intend to collaborate on indoor positioning solutions and how this gets rolled out into the handset market. So this deal with Samsung was more than just a point transaction. We'll be working together to really try to optimize the solutions and the consumer experience in the handset space. Okay, so moving to the next slide, let's take a kind of high-level view of where we see applications for indoor positioning. And we think that it's very broad. Handset is the most obvious market. I mean, any kind of searching or tracking or social networking will inherently work better with higher quality positioning indoors. I mean, in a shopping mall, I think today the location experience falls a pretty long way short of consumer expectations. And there's many other applications such as geotagging pictures. Today none of these cameras really give you a good position fix indoors. Fitness devices, whether you're running outside or you just want to keep track of calories burnt indoors, it would work a lot better with a good quality location. But another large growth area for indoor location is asset tracking. We see a lot of applications in the future for small devices attached to things that you really value, maybe your laptop, your car keys, and all of these products will greatly benefit from having indoor location. So we see a very strong market demand, and we're working on technology that can satisfy that demand. So moving to the next slide, introducing Surf Fusion. So Surf Fusion is a technology that combines phone sensors within the phone, such as accelerometer, gyro, compass, and barometer, together with Wi-Fi signals to do indoor positioning. And if available, we can use GNSS signals as well. And by combining these three different technologies, it allows us to do positioning and 1 Hz navigation indoors. And that can then go on to fuel a whole raft of applications that layer on top, providing good quality location-based services. The other point is that by combining these technologies together, it also improves our outdoor performance as well. So it isn't just indoor performance that improves by combining the technologies. So moving to the next slide, a little bit of a look at our next generation location platform. So there are two components to this solution. One side is a server-based, cloud-based technology, our CSR positioning center. And then there's the device side with our Surfstar 5. And the Surfstar 5 chip combines quad GNSS, so compass, Galileo, GLONASS GPS, together with a MEMS gateway to control MEMS sensors, pedestrian dead reckoning technology, and a second radio to receive terrestrial and satellite-based signals. Now, this second radio is capable of receiving Wi-Fi, GSM, ComLab signals, Boeing XGPS. There's a wide variety of signals of opportunity that we can utilize to improve on indoor location capability. So moving to the next slide, taking a little bit of a deeper look at our GNSS capability. So we're targeting the 4 main systems plus all the satellite-based augmentation systems. When we have corrections from SBAS, they're available. And we've also put a lot of work into handling multipath and interference techniques to have a reliable solution at all times. And we're really pushing the boundaries of sensitivity in that we can track SATs down to -165, and we nav at about -163 dBm. So moving to the next slide. Now this is starting to look at some of the results of how GNSS helps us with indoors. And the bottom line is that although GNSS improves the coverage very slightly, it doesn't really give us the type of accuracy we need. So on this slide, you can see in the picture there that more than half the fixes were outside of our building. And this is a walk test in our Sunnyvale office in Silicon Valley. And frankly, the positions that are just coming from GNSS put us in the vicinity, but they don't really put us where we are actually within the building. And it's interesting to see the difference between GPS and GPS plus GLONASS. And as I say, the bottom line is GNSS on its own is not enough to solve this problem. So moving to the next slide, in the demonstrations that we've been showing of this technology, we've used ST sensors, and we have what's called 10 degrees of freedom. So we have a tri-axis accelerometer, magnetometer, gyro, and barometer. So these raw outputs from the sensors are captured by our device, synchronized, and we run our own calibration technique on the data. We can use the data to determine the context of the user, such as walking or running, and we use footstep detection rather than just integration of position to decide our pedestrian dead reckoning solution. The problem with pedestrian dead reckoning on its own is that the error grows around 10% of distance traveled, and it doesn't recover. So really, it's a technology for smoothing and bridging between absolute fixes from a different technology. Next slide. So our different technology here is Wi-Fi positioning, and we use the Wi-Fi capability to give us absolute positioning. And we learn with our back-end server centroid locations of access points. And we crowdsource that data. So this system is self-learning and self-harvesting. When you walk through a building for the first time, it's learning the Wi-Fi contours, and it's very dependent on pedestrian dead reckoning for positioning. And that data goes to the server and goes on to create a tile that aids the handset calculate position. So performance is slightly variable. It depends on how many people are in the environment, how much Wi-Fi coverage you have. But we're going to show some slides shortly that show the types of performance we've been achieving with this technology, and it's very encouraging. Okay, so next slide. Major components of Surf Fusion. So as we've discussed, we have GNSS capability, which gives us some coverage indoors as well. We have a self-learning database, which provides us with data that we can download as a tile to the handset. We run Wi-Fi scanning within our chipset, and that lets us do Wi-Fi positioning. And we use MEMS sensors for pedestrian dead reckoning. And we combine all of this at the Kalman filter level to give us continuous indoor positioning. So moving to the next slide, the test platform. So in this example, we used a HTC phone, and we put in a smaller battery and grafted in a small circuit board at the back. And pictured there, our little circuit board has the 5XP chip with flash and the different MEMS sensors to complete the solution. And on the right-hand side there is just a capture of the phone positioning us indoors in a conference room in a hotel. So at this point, I'd like to hand off to Blake Bullock to present the results that we've been achieving with our Surf Fusion product.
Thank you very much, Dave. So with this Surf Fusion system, we were keen to test it in real-world situations, and we've taken this demo device with the actual software and sensors for Surf Fusion. We've taken it to very challenging environments throughout the world, including indoor shopping centers, train stations, convention centers, airports, and we've really tried to challenge the capabilities of the system in testing in real-world environments. We've noted that for example, in train stations, you can have a high number of Wi-Fi access points that are available. You can have a lot of magnetic anomalies. You can have a lot of moving people. And these are very, very challenging to get consistent Wi-Fi signals and magnetic readings. And so we believe are some of the most difficult environments for indoor positioning. The test case that we're going to share with you is from some testing that was done in Tokyo Station earlier this summer in downtown Tokyo. And we've got an indoor map here overlaid on Google Earth showing the geometry of the shopping area inside Tokyo Station. And this is a couple of levels down, and it's below the track level, below the street level, so it's very deep indoors. There's absolutely no GNSS signal available. You can't track even one satellite, no windows. So you're completely relying on other technologies for your indoor positioning. The chart that you're seeing right here has a number of different tracks. First of all, the path that we walked is the straight green line down the middle aisle. Then the red squares are the position fixes obtained through Wi-Fi positioning alone. And you can see that position jitters quite a bit. This is due to fading and changing signal conditions from buildings and moving people. It's also not a continuous signal. In our situation, we were getting quite frequent fixes, but in many mobile phone devices, you would not be able to get fixes quite as frequently. The pedestrian dead reckoning solution is the yellow line, the yellow series of dots rather, and as you can see, when you do not have any absolute positioning, that path tends to wander off, and in this case it started wandering off to the left, and it came back a little bit, but generally it tends to drift away over time. As the further you walk, the further it deviates from your actual path. The blue triangles is the Surf Fusion solution, which is the blended result of the Wi-Fi and the pedestrian dead reckoning. And you can see that it follows the path generally. It stays within a few meters of that green line. And even after several minutes of walking, you can see that it's staying true to where it should be. And that's the effect of the Wi-Fi providing an absolute correction. The next slide shows another walk test in the same general area. This time the flags demarcate the path that was walked, and the blue series of triangles is the surf fusion output. We wanted to make sure that the surf fusion could react properly with turns inside these narrow corridors. These corridors are only about 2 meters wide in this area. It's kind of a cramped shopping area, and so it's just to give you an idea of the scale. As you progress along, it successfully detected every single turn properly. It deviates from the path by a maximum of about 7 meters, and this test was about 6-minute walk altogether. This next slide, again, is in a similar area, but a different walk test that was performed, again, about a 7-minute walk. The flags mark the path that was actually walked, and you can see that the surf fusion detected all the turns and kept the result fairly close to the corridor that was being walked. I might note that there is no map aiding or map matching going on in this solution. Map matching and map aiding are ways of further improving the position output, but this series of tests is aimed at detecting the absolute best performance of the positioning without any map aiding or map matching. And then to test the repeatability, we did that same walk 3 separate times and did a cold start at the starting location. In other words, we turned off the positioning system and turned it back on, so it has no knowledge of where it is. It has to get its initial fix from Wi-Fi alone, and then start the walk. And you can see that the 3 green paths overlaid onto each other match fairly well, showing good repeatability for the surf fusion solution. These results are very encouraging, and in a separate test we did some benchmarking to see the accuracy level. We would go to spots within a mall that was well known lat long, and we would take our measurement there, and you can see the cross-track error here, and 68% were under 10 meters cross-track error, and this is very encouraging. So surf fusion is a solution that determines position indoors, and it can handle the transition areas going from indoors to outdoors. This solution does not require any additional infrastructure for building owners or store owners to install. It's based on sensors that are already there, namely Wi-Fi. The solution does not require manual surveys ahead of time. It's got a self-learning system to adapt to changing environment over time. The position availability indoors approaches 100%, and the accuracy is exceeding our target of 5 meters, 50%. This is a solution that's suitable for mobile phone handsets, cameras, tracking systems, and various other small electronic devices, and really starts to show the power of what can be done indoors, and enabling an ecosystem of experiences for consumers. Alan, back to you.
All right, thank you, gentlemen. We'll move next to Chris Gates, who's VP of Corporate Strategy at NextNav. NextNav, as you can see from the slide on your screen, is focused on high-precision urban and indoor positioning services. Chris has more than 15 years of experience in finance and telecommunications. He joined NextNav from Skyterra Communications, where he served as VP of Strategy. He has extensive experience in wireless and wireline communications. He holds a Bachelor of Arts degree from Dartmouth College. Chris, the floor is yours.
Hi, Alan. Thanks. For the, I think for the room, it may be worthwhile just to give a brief background on NextNav, formerly known as through about the middle of last year as ComLabs. We've been developing what we characterized as a terrestrial GNSS constellation, which is a little bit of a paradox, but effective for the past 4 years, including the development of the network technologies necessary to deploy a high-precision terrestrial positioning system that offers wide area coverage, that is, as opposed to venue-based coverage, on a managed network basis, and deploying or commencing the deployment of such a network and undertaking the various ecosystem activities that are necessary to get that going. So, as everybody knows, the key issue, and I think CSR and Samsung did a nice job introducing this, the key issue with GPS and GNSS solutions, of course, is that while they're excellent positioning systems, when you have visibility to the satellites, they tend to degrade or become unavailable in indoor environments, and particularly as we get into urban areas. There are some other issues associated with GNSS technologies as well that perhaps inhibit their use in consumer electronics devices, the most significant potentially being in cold start modes or in modes when you lose visibility to the satellites, a longer time to first fix, and of course the power draw issues associated with particularly weak signal environments. Another consideration in complex indoor environments that legacy GNSS systems have had challenges dealing with is providing very accurate height information, particularly in complex structures where context becomes highly associated with what level you're on, such as a mall environment, an apartment building, or a multi-use building in an urban area. The ability to distinguish between different levels is something that we think is critical for a great pedestrian and indoor navigation positioning solution. So some of the considerations that we've sought to address with our system, of course, are the accuracy required for indoor environments, but also to provide a universal capability across an entire metro area and eventually across a continental or a countrywide area. Localized solutions such as are available today, and I think there are solutions out there that have been deployed in the enterprise that have addressed indoor positioning with a high degree of accuracy, but they tend to be cost prohibitive for wide area deployments, and they don't provide the level of pervasive reliability that's really necessary to build consumer confidence in use in those types of solutions. Cost considerations have been critical for dedicated positioning systems, whether it's in the form of infrastructure expense or receiver complexity or coverage scale, which are the 3 notes that we have on there. There have been a number of entities that have attempted to address various elements of these issues. At NextNav, what we're trying to do is address all of them, and we'll talk about how on the next slide, the next couple of slides here. Other key issues associated with some of the solutions that have been deployed that do provide some indoor positioning capabilities, although perhaps not with the level of performance that's necessary for a great consumer experience, are sort of based on network architecture issues. For example, recycling cellular networks to attempt to provide a location solution. Cellular networks aren't architected for location. They suffer from, in many cases, poor geometry, poor synchronization, and various other issues, poor site location, for example. Overloading facilities designed for other services really hasn't quite yet yielded the level of performance that we would hope. There are certain areas where Wi-Fi provides exceptional performance, but those areas tend to be limited. And I know in the U.S., people that are developing consumer applications, based on the discussions we've had, are really targeting kind of the 100-meter level for indoor location accuracy as a reliable metric to work with. Of course, in some areas, we see performance that's significantly better than that. In some areas, of course, we see performance that's significantly worse. But 100 meters is kind of, I'm in the mall, I'm on this city block, not I'm at this venue on this level. and therefore my context is this, or show me the path, show me the blue dot on the path that gets me from location A to location B inside the structure. So the next chart that we wanted to talk about, this is a chart that we've actually been using for several years, and it's interesting because we have yet to have material cause to really update it. We're familiar with the performance of assisted GPS and GPS in mobile devices, and we see some of the coarser technologies that offer wide area service, cell ID based technologies, the UTDOA technology that some cellular carriers have deployed. But there's this missing piece that provides that venue level accuracy indoors in an urban environment. So the way NextNav is attempting to resolve this, and this is a fairly complex slide, and I'm going to spend a few minutes on this. So if you'll bear with me here, what we're doing is we're deploying basically a terrestrial positioning constellation. There's a high degree of technical commonality with GPS. Both in terms of the core signal structure as well as the principles of location that we've adopted. So this provides what amounts to a reference radio network. It's an overlay network, so it isn't affiliated with any particular wide area deployment out there today. The core components are highly synchronized beacons where our transmitters are synchronized to the single-digit nanosecond level using some technology that we've developed. The signal itself, as we said before, is very similar to GPS. It shares an identical channel bandwidth and similar data structures. Obviously, there are some differences because operating a terrestrial network does have some differences from a space-based network. We operate on licensed spectrum, which allows us to offer broad coverage from a small degree of sites, so it's economical for us to deploy a network and offer service to mobile devices. And we've developed some proprietary algorithms and techniques to address the issues associated with terrestrial location, like a harsh multipath environment and related issues. The performance that we've seen, and we'll share a CDF or a cumulative distribution function of accuracy on our initial system from on a network-wide basis, is GPS-like in the horizontal domain, but we've also developed a technology to offer accurate vertical position in the 1 to 3 meter range. Time to first fix from a flush start basis on a cold start, from a flush cache basis on a cold start is on the order of 6 seconds. Obviously, warm start or continuous tracking is at that 1 second level. And importantly, it's a fully managed network that's designed, deployed, and operated exclusively for location. The reason that I mentioned the technical commonality with GPS is to ensure that the technology can be incorporated at a reasonable cost into mobile devices, and particularly cellular handsets. Although, of course, the incorporation of our technology into asset tracking and other consumer electronics devices, enterprise tracking devices, is clearly something that we're very interested in. At the digital baseband level, it really does look to a large extent like a GPS chip. Of course, the chip itself would have to be able to accept our signal input. We are operating on our own frequency licenses, which are different. It's a different frequency band than the band the GPS occupies. But that does allow us to leverage some amount of the significant work that's been done in GPS silicon already. So it's not a standalone. It's not a separate chip solution. The handset integration then looks very much like band support as opposed to adding new silicon to the device. So this allows us to offer a wide area solution that provides GPS-like performance with the critical vertical position capability on a cellular device at reasonable cost, with limited power consumption, and of course the on-device computation of location, which has a number of important implications. And the fact that the signal looks very much like a GPS signal and is delivered using silicon that is specified for GPS allows us to leverage many of the existing elements, application call flows that already have been deployed. It looks more like a configuration than a massive integration effort on the application and core network side for folks that want to adopt the technology. So we'll share a couple performance charts with you. On slide 6, excuse me, not slides. Let me move ahead to the next slide here. I'm sorry, slide 25. What we see here is a CDF, and this is a CDF across the San Francisco Bay Area of our existing system as it stands today. So we characterize the performance here as a 20 to 25 meter performance at the 50 to 67% level. We're actually conducting, this is indoor performance only, and it represents a variety of structures and a variety of morphologies from highly urbanized zones and deep in buildings, elevator shafts and so forth, as well as areas with lighter construction. We're actually working on some advanced technology that will be rolling out in the second quarter of this year. We anticipate rolling out in the second quarter of this year that should move this to the left by about 50%. So we anticipate demonstrating a 10-meter solution in the first half of 2013 using our existing network capabilities. As we move to slide, I apologize, move to slide 26 here. We were also demonstrating consistently across our deployed network area floor level height accuracy. And what we see on this chart are tracks from a receiver that were taken inside. This is the Intercontinental Hotel in San Francisco, which is a significant structure because it's a complex structure. It's in an urban environment, and of course it has a large number of floors that are closely spaced. So what we see is a test engineer moving through the facility on 2 separate days, where the x-axis here is time and the y-axis is height. And what we've done is we've overlaid the track on a building model, and you can see that at each step, whether riding down the elevator, which are the vertical lines, or walking downstairs, which are the more jaggy lines, you can see the test engineer transit from the 20th to the 15th floor on the red line, and on the blue line. And on the blue line, an elevator ride down to the 10th floor, and on the red line, walking down steps to the 14th, and then the 12th and 11th floor, and so forth. So we're very pleased with to be able to demonstrate this level of performance, and we do think it's critical to great indoor navigation. So just to summarize, we are seeing greater adoption of location in consumer applications, but also in the enterprise. A critical application that we haven't mentioned in a great level of detail and haven't discussed on this call, but I'm sure has been addressed elsewhere, is the importance of indoor location for E911. I think it was referenced by Alan in the introduction that the FCC is currently conducting some tests to inform an E911 process that we anticipate moving forward in 2013 with side-by-side trials of some of the different what we characterize as wide area / carrier grade technologies. That is, technologies that can be managed end-to-end and technologies that can provide emergency service capabilities. So we're deploying what we consider to be a revolutionary wide area positioning system. It's effectively a fixed reference network of transmitters that look very much like terrestrially based GPS satellites, although of course we do have our own spectrum licenses. We're basically attempting to bring carrier grade ubiquity and reliability and accuracy to indoor locations such that it's available everywhere in the same way to pretty much everybody that has a mobile device. And so with that, I'll hand the floor back over to Alan.
All right. Thank you, Chris. We'll move next to a presentation from Spirent Communications given by Manikantan Parameswaran, who's a senior application specialist at the company. He initially joined Spirent in 2006 and has worked on a variety of different AGPS protocols and technologies. He holds a Bachelor's of Science in Computer Engineering from Drexel University. Mani, take it away.
Thanks, Alan. Hi, everybody. Before I continue, a brief note on Spirent Communications. We are a test equipment manufacturing company, and we serve both wireless and wireline and network markets. In specific, for the past several years, we've been very involved in testing both GPS and GNSS, both from the conformance, performance, and also the R&D side. Today, I'd like to talk about some of the challenges of deploying indoor positioning and test strategies to overcome these challenges. So in our view, there are two major drivers for indoor positioning. There's the regulatory driver that Chris touched on just a little bit ago. The FCC has had for several years what's called the emergency mandate. So location is required when somebody dials a emergency call. Now it turns out a lot of these emergency calls are coming from indoors where GPS has a hard time being visible. So the FCC is particularly interested in finding the 3D position of emergency callers. The other driver, as speakers before me touched on, are a host of commercial uses. Deploying indoor positioning on mobile phones and a broad range of devices is going to be quite useful. Many different apps can be enabled by deploying this on mobile phones, like check-ins, social media, and also there are prospects for a lot of data collection for customer relationship management. So essentially what we are seeing right now in the market is location technologies are moving on from purely depending on AGPS and GNSS to add other technologies. Spirent is following this evolution. Our test systems are moving from just supporting AGPS to add additional technologies to support indoor positioning. So a quick word on the technologies involved. Now there are a variety of technologies that can be used for deriving a position and navigation indoors. There are the technologies shown on the slide: GNSS, Wi-Fi, cellular, and MEMS-based navigation. There are also additional systems like Chris just talked about. Spirent, from our point of view, we are focusing on these four technologies, mainly because they're mainstream, they're scalable, and they're available right now. You don't need significant new infrastructure upgrades. These cellular, Wi-Fi, and sensors, they're all on mobiles right now. And in fact, with the exception of GNSS, these other technologies are being used for other purposes. So there's a lot of efficiency in repurposing them purely for location. So the speakers before me did a great job in presenting the technologies. I'm just going to provide a very brief overview of each technology. So GNSS everybody is familiar with, and it's really good outdoors. You get very highly accurate positions. But indoors, the challenge is receiving signals. Wi-Fi positioning is good wherever there are clusters of access points. So that implies that they're good in indoor locations like malls and urban settings. Not so good when the number of access points are far fewer, so like in the suburbs or on highways and so on. Positioning using the cellular network can be ubiquitous wherever the cellular network is available. The positioning techniques vary, though. You can use coarse techniques like cell ID and enhanced cell ID, or sharper techniques like time difference of arrival, and also it depends on the kind of cellular technology being used. And finally, MEMS sensors-based navigation. It uses a process called dead reckoning, where the sensors can actually use an initial position perhaps from GPS or some other technology, and then sort of step through and add additional positions based on the output from devices such as accelerometers and gyroscopes. Typically, sensor positioning is very accurate. However, there is a drift over time. So moving on to the next slide. The challenges of deploying indoor positioning. In this slide, we're showing you a mobile phone. Let's take that example. So if you want to deploy these four technologies to find a position, not only do these four technologies have to work well individually, but they also have to interact well together. The need for the interaction is what makes indoor positioning, what drives indoor positioning. The mobile actually has to detect the environment, monitor the signals that it does receive, and then select the right technologies appropriate for the situation. Let's say you walk from outside into a mall. Outside there was GNSS available, but as soon as the user walks into the mall, the mobile must be able to detect the change and then select the right combination of technologies to address it. In fact, in some malls, there may be skylights and windows and so on where there is GNSS visibility, and the mobile must be cognizant of that and take advantage of GNSS whenever available. There's also interactions between technologies. For example, in the crowdsourcing use cases, Wi-Fi access points and signal readings may be reported back to the network with the geotag. And finally, the positions from the sensors and GPS may be input into a Kalman filter to derive the overall position. While all this is happening in the mobile, the mobile is also talking to a network server outside in order to get assistance data and do position reports. And finally, in the midst of all this, a mobile device also has to handle everything else that happens: voice calls, data use, maybe application use, music, and so on. So in order to ensure good performance, you need a comprehensive test strategy. And there are two major test strategies. There's field testing and lab testing. So I'm going to walk through each one of them with some examples and strengths and weaknesses. To start with, we have field testing, where the tester actually goes out into the field with the device under test and exposes it to field conditions. Now, this is the best way of understanding how exactly the device performs in the user's hands. You'd pick like malls, train stations, the examples shown, talked about by the other speakers, and you would collect data and understand what are the trouble spots and where the most difficulties are encountered. Now, field testing is very critical, and also there are a couple of challenges, though. First, the field environment is out of control from the tester. It's not repeatable, and things keep changing. There may be additional access points being added. Somebody might create a window where there wasn't one before, and so on. It's also time-consuming and expensive. Now, the other test strategy, lab testing, involves using different instruments to simulate the signals in the RF of the location technologies in question. So you would have something that creates a GPS environment, something that does like a Wi-Fi access point emulation, and so on. So the advantages of lab testing are you can create a scenario with all these interpositioning technologies which is perfectly repeatable, and you're in complete control. You can vary signal levels and so on. And finally, the other advantage is automation. You could set up a test scenario, let's say on Friday evening, let it run over the weekend, come back on Monday, and you have a report ready. Lab testing does have one challenge, though. While you can create the signals in the RF necessary, and come close to how things would look in the field, you can never replicate the field exactly. So as you can see, these two test strategies are actually complementary to each other and should both be a part of an overall test strategy. Now, lab testing itself has two modes, a simulation mode and measure and playback. So moving on, I'd like to talk about the simulation mode first. In simulation, you use your simulators and to basically construct a test scenario. As an example on the slide, there's a map of the Monmouth Mall, which is pretty close to the Spirent office. The red dots actually represent the user trajectory. So you could put this together and then select the technologies that you want interacting with the device. In this case, there is GPS on the sides outside the mall. There are a couple of cell towers. There's a bunch of Wi-Fi access points inside the mall. And finally, there's a sensor profile for the user. For example, the user could be walking upstairs or running and things like that. Suppose you could set all this up in a test scenario. You would be able to repeat this multiple times and change things to understand how the device behaves while if certain elements are modified. For example, you could keep all the other signals constant and just remove some of the Wi-Fi access points, see if there's any difference in performance, and so on. So why use simulation? The main use is for initial test development. You would basically have you could use a simulation to test how well the device responds to various types of changes that you could do in your test scenario. As an example, I'm showing a multi-level building on this slide. There are access points located on various levels. There may be limited GNSS visibility through windows or maybe a skylight and so on. So in this simulation, you can determine things like, is there any optimal arrangement of access points that influences positioning? is it better to have them in a certain clusters or in a distributed evenly and so on? Will the mobile be able to take advantage of any GNSS that is visible, that sort of thing? So moving on to the next mode, we call it measure and playback. So this mode is sort of like a hybrid between field and lab testing. In this mode, the tester actually goes out to the field and captures signals from the technologies of interest. So the idea you could capture technologies by sampling or by measuring signal levels and so on. This stuff is then processed and then fed to simulators to replay it. So you get an output close to the field, not exactly, but close. The main advantage of measure and playback is it reduces the amount of time actually spent in field testing, especially for very challenging scenarios. So I have an example here, the Tokyo station, which CSR also touched on about, and purely coincidental, I assure you. Let's say the user, a real-world case where the user has to enter the train station and has to catch a train in like 5 minutes. He needs to navigate inside, and it has to be seamless. So the mobile had GPS or GNSS outside, but as soon as it enters the station, you're likely to be completely cut off and need to depend on alternate technologies to get to the train. And so it's a high-stress case. So in this, if this situation could be recorded and measured and played back in the lab, there could be a lot of time savings in device validation. You could expose a number of devices to the same scenario and benchmark the performance. You could measure the effect of having different types of software updates on the device and see if anything changes. So to summarize, indoor positioning uses multiple technologies interacting in complex ways in order to derive position and to perform navigation. A comprehensive test strategy for optimizing the positioning and navigation should require both field testing and lab testing. Lab testing itself can be done in two ways, via simulation or via measure and playback. Simulation is useful for initial development, and measure and playback for reducing time spent in the field and device validation. We also have a bunch of collateral written on this subject. I invite you to follow the link over there. At this time, I'd like to turn it back to Alan for a Q&A session.
Thanks very much, Mani. We have a broad assortment of questions. We won't have time to get to all of them, but we will take them up after the webinar, and I'll return at the end to tell you just how we are going to address those. The first question concerns mapping. Now, Blake mentioned in his presentation map aiding and map matching, although they were not used in the trials that he talked about. They're going to be maps, indoor maps are going to be necessary at some point if indoor navigation is going to become a reality. Can any of you gentlemen step outside your presentations or your specialties for the moment and speculate or tell us what you may know? How are conventional navigation mapping companies moving to adopt indoor mapping or adapt themselves to the indoor navigation business? And if anyone can respond to this.
Yeah, well, and this is Blake. We've got some experience in this area. I'd be glad to take that one. Although we're not using map aiding and map matching in the current round of tests, we are using maps for rendering to the consumer. It's a very important part of the visualization and the whole user experience. So we've been partnering with various companies to facilitate that. And as we've done a scan, we've looked at the traditional mapping companies, which are TomTom and Navtech, that have been doing digital maps for vehicle navigation. And Navtech for the last 2 years has been very aggressive in creating indoor maps using the same sets of tools and processes that they've used before, but adapting them to the unique challenges of doing indoors. TomTom has not been very active in this area yet, and then you look at the two other main mapping companies that most people are familiar with is Google and Apple. Google has been also very aggressive in creating indoor maps and also in enabling consumers and business owners to put indoor maps up onto Google Maps, basically user submissions. And once you submit a floor plan and show where it's supposed to go, it can appear on Google Maps, which is a tremendous tool to help speed things along. But there's a trust and reliability aspect that introduces. Haven't seen anything on Apple Maps yet as far as indoor mapping, and as they use the TomTom map data as their base data, it's not surprising. But I would imagine that Apple will get into that feature set in the future as well. The key thing is capturing the geometry of the walls and the doors and the escalators and elevators is very important and useful for both visualization and in positioning for indoors.
Yeah, I would add to that. There is one other group out there that's been pretty aggressive on indoor mapping, and that's Micello. One of the things that's emerged, this is Chris Gates from NextNav, one of the things that's emerged or that we've seen is that the set of skills that are required for indoor mapping are somewhat different than those for indoor mapping and navigation are somewhat different than those required for outdoor mapping. And you get into a question of just simply the availability of the interior geometry of the building is a challenging issue to resolve. The other thing that of course becomes very important for indoor structures, once again I'll emphasize, is the importance of accurate level information, which is something that's emergent but is somewhat difficult to mechanize, I guess is probably the best way to put it. And the ability to mechanize that indoor mapping process is something that'll be pretty important going forward.
Yeah, right. Thanks for bringing up Micello. They're not a conventional mapping company, but yeah, they are one of the new breed of indoor companies, and several others that are creating indoor maps, focusing on those.
Yeah, to briefly add to that, I believe Microsoft is also working on doing the indoor mapping. In fact, the slide I had with the map for the Monmouth Mall, there was a much more detailed version of including like stores and whatnot from Bing Maps.
Sounds like this is going to be an active area, an active opening up area. We have another question from a listener. I'll ask Dave. Dave, this listener wanted to know what was the battery consumption during the trial runs in the Tokyo station?
Yeah, so let me address that question. The power used during those trial runs ranged between about 25 to 75 milliwatts. And the reason for the variance in power is really that it's very dependent on the context of the user and whether or not they're moving. So if we detect periods using the MEMS sensors where you're stationary, then we shut down the radios that we don't need for positioning. So it's a very dynamic power level depending on the exact use case. And one other aspect of the power question is that because our solution is a self-contained chip that calculates all the way up to your latitude and longitude within the chip, we don't absorb host application processing power consumption while we're doing positioning. So compared to a host-based solution, we believe we're very power competitive.
All right. Thank you, David. Third question. Somebody out there, obviously an erstwhile developer, how does an Android or iPhone app development company take advantage of SurFusion or NextNav? Is this a reality currently or something to just put on your 10-year plan?
On the SurFusion side, it's not a reality, and it's not on the 10-year plan either. We think it's much sooner than that. The intention is to embed indoor positioning into mobile handsets and make those available for application developers just the same way that the positioning API, the location API is available today. I would suspect that in the near term, we'll see indoor positioning actually as an application first, and the capability for indoor positioning would be made available to other app developers through an SDK from one app developer to another. But then in the not so distant future, certainly not 10 years, we would expect the indoor positioning to be actually embedded in the phone, and app developers would be able to access that just the same way they access GPS positioning and Wi-Fi positioning today through an enhanced API that handles indoor.
Yeah, and I'll just briefly answer the first part of that question. I think very similar to the incorporation of the Surf Fusion platform. Our technology does require it does have to be incorporated into a mobile device before it becomes available, and we anticipate that happening certainly not on the 10-year horizon, but significantly sooner than that. And then similarly would be made available through an API that allowed access to our technology.
All right, thank you, gentlemen. Ladies and gentlemen of the audience, we have reached and even surpassed slightly our 1-hour mark. It's been a very informative webinar. I hope you share my sentiment on that. It will be available for download probably sometime next week. If you go to gpsworld.com/webinar, the place where you registered for this webinar, you should find a place to click and download both the slides and audio portion of the webinar, and you will be able to forward that also to colleagues who you think might be interested. There were many questions that came in during the webinar. We had time only to address 3 of them during our webcast, but we will return to these questions. I think I'm going to share all the questions with all the presenters. We'll collect their answers and provide that. I think it's very likely that that will be published as part of my system design newsletter either probably in January, and we'll make an announcement on gpsworld.com and in the Navigate weekly e-newsletter as to when the answers to those questions will become available. You can subscribe to both newsletters, mine and the Navigate weekly, at gpsworld.com/subscribe. Finally, I'd like to again thank our sponsor for the entire webinar series this year, 2012, and this one, of course, Hemisphere GPS, and thank our presenters for sharing their knowledge and insight, and thank you, the audience, for attending. And for now, this is GPS World and Alan Cameron on behalf of all of our speakers signing off. Thank you for attending.